So now what will be the expected velocity profile? Now, as we can see, the expected velocity profile is drawn here. Now, the velocity at the wall will be zero because of no slip boundary conditions. Velocity at the wall will be zero because of no slip boundary condition, and as temperature for the heated plate is higher, the molecules here will rise up. And similarly is the case of the cooled plate. Now, as again the same here, the molecule will have zero velocity at this point because of no slip boundary condition. And as their temperature is lower, the molecules here will move down. And since the velocity here is positive and here it is increasing, and now the velocity will be in negative direction here. So somewhere in the middle, the velocity will be zero. The velocity will be positive here and increasing, and at some point it will become zero and then it will be negative. So this will be the expected velocity profile. Now the net mass flux over this complete region, if I take a net mass flux at any cross section over this complete region, that is from minus b to plus b, it will be always zero. Now we will apply the shell momentum balance equation or equation of change. For that, we have these equations. Now, why we will use the Cartesian coordinate equations? Now, we will be using the Cartesian coordinate equations because this is a rectangular box, and in this rectangular box, our system will be easier in the Cartesian coordinate. Our equations will be easier in the Cartesian coordinate system. Now, next is why we will only consider the z equation of motion and not the x and y equation of motion. The x equation of motion is not considered because there is no variation of velocity in x direction. And y equation of motion, variation in y direction of velocity is not considered because in y direction also there is no variation of velocity and end effects are neglected. And therefore we will be considering only this z equation of motion. And now in this z equation of motion, we will be substituting tau xz using the Fick's law. So substituting the Fick's law here, we will get this equation. Now in this equation, we have a lot of terms that are zero. Now let's see one by one which terms are zero and which terms are non-zero. Now first term, that is dou vz by dou t, is zero because of steady state. Our system is assumed to be at steady state. Next term, Vx into dou Vz by dou x is 0 because Vx is 0 and also Vz is not varying in x direction. So this term is also 0 and this term is also 0. So overall term is 0. And also again end effects are neglected in this case. Now Vy into dou Vz by dou y. Now this term Vy into dou Vz by dy is equal to 0. Because Vy is neglected. Vy was neglected. We have already discussed it in the previous section. Why Vy is neglected? Because of Vy is in very small region. That is 2b is much smaller than length. And Vz is varying in y direction. Vz is varying in y direction, but since Vy is 0, the overall expression will become 0. Now next is Vz dou Vz by dz. Next is Vz dou Vz by dz is equal to 0. In this, Vz is not varying in z direction and effects are neglected. And also, Vz is also 0. Vz is non-zero. So the overall term becomes 0. So last term, then we have next term as dou p by dou z. This is not 0 because of buoyancy forces. Now, as we have seen earlier that Due to temperature changes, that is temperature difference, higher temperature and lower temperature, the density of the liquid is changing. And due to difference in density, there is buoyancy forces, induced buoyancy forces. Now, these induced buoyancy forces are there, therefore, dou P by dou Z is not zero. Next is dou square Vz by dou x square is equal to zero, because again Vz is not varying in x direction and effects are neglected. We have already seen in this previous slide. Dou square Vz by dou y square, it is also not zero because Vz is not varying in y direction. It is not zero. Dou square Vz by dou z square is equal to zero because Vz is not varying in z direction and effects are also neglected is the reason. And last term is rho gz. It is not zero because gravity is there and it is acting in minus z direction. This is our positive z direction and gravity is acting in minus direction. So this is our positive z direction and our gravity is acting in minus z direction. So gz is not zero. So after substituting all the zero and non-zero terms, we arrive at this expression, that is rho d square Vz by dy square is equal to dp by dz plus rho g. After neglecting all the zero terms, we will have only three terms which are non-zero. That is this term, which is minus dp by dz, and this term, dou square v by dou y square, and this term, rho g into z. So these three terms, yes, yeah, these three terms, this term, and this term, they are non-zero. So if we arrange, and one more thing we have to take into consideration here, which is that G is acting in this direction, but our coordinate system positive direction is this. So G is acting in the negative of our direction. So we can write that Gz is equal to minus G. So after taking this into consideration, we will have our velocity profile equation like this after writing the non-zero terms. That is mu into dou square Vz by dy square into dp by dz plus rho g. Now we have to integrate this equation. The thing is, we cannot directly integrate this equation. Why we cannot directly integrate this equation? Because see, this term is constant, but this term, density term, is not constant. Because the temperature change happens due to which the density changes. And due to the density change, the buoyant force occurs, and due to this buoyant force, only the movement of the molecules are happening. So this term cannot be zero. Sorry, this term is not constant, and we have to find some expression for this rho term. That is, we will find it from thermodynamics, and from thermodynamics we find this expression that rho is equal to rho at T is equal to T bar. That is at average temperature, and d rho by dt at T is equal to T bar into T minus T bar, and after that we will have d square rho by dt square into T minus T bar whole square, and so on and on, but we will neglect the higher order terms. Now this expression, it comes from the Taylor series. From Taylor series we get this expression, and it is a general mathematical series that at certain point, if we know the value of a certain function, then at the nearby point we can find about it using this approximation. So from this approximation we will have our equation, and we are neglecting the higher order terms. So after that, this can be written as rho bar minus rho of b, rho bar into beta bar into T minus T bar, and again we will have the higher order terms. Again we will be neglecting the higher order terms. Now what is beta? Beta is given by this function, that is 1 by v into dou v by dou t at some pressure P. V is the specific volume, and V can be written as the inverse of density, reciprocal of density.
So we will write it like this, and if we integrate it, we will get minus 1 by rho square term over here and d rho by dt, and this will get cancelled and we will have this final value. So what is beta? Beta is said to be the coefficient of volume expansion, and beta can be said as a relation between the temperature and the density. So beta is a relation between temperature and density. And again, buoyant force. Buoyant force, as it is dependent on temperature. Temperature causes the buoyant force, which leads to change in density. So we can say that the temperature depends on density, and the density depends on beta. So temperature also, we can tell that it is somewhat of a relation which will contain beta. So again, what we will do is one more thing is rho bar and beta bar. These are density and coefficient of volume expansion, which are evaluated at the average temperature. That is, the rho bar is the average density, and beta bar is the average volume of coefficient of volume expansion. Now, now what we will do is we will substitute the temperature profile in the velocity equation. That is, in the previous slide, we had the equation of velocity after substituting rho. In that, we will substitute our temperature. And after substituting the temperature profile, we will get this equation mu into d square vz by dy square into dp by dz plus rho g plus 1 by 2 uh, rho bar g into beta bar delta t into y by v. Now here we are getting the velocity as a function of distance y. Before, what we had, that we had velocity as a function of rho. Now we can see that rho is a function of temperature, and temperature is a function of y. So from those relations, we got that Vz as a function of y. Now the main major components are the viscous force, that is the viscosity, the pressure gradient, and the gravity. Gravity is one of the driving force of buoyancy as well. And the temperature driven buoyancy, that is delta T beta. It will depend on delta T and beta. Now we will be integrating this equation. So we have this second order linear differential equation, which is d square vz by dy square is equal to c1 plus c2. For simplicity's sake, we assume this constant to be c1 and this constant to be c2. So after assuming this is c1 plus c2y, we will integrate it once. Sorry, before integrating it once, we will first send the mu over here. So it can be written like this. And after integrating it once, the y term will come. Here y square by 2 term will come. And this is the constant, first constant. And again, if we integrate this, we will get the velocity profile. Again, here y is there, so y square by 2 term will come. Here y square by 2, it will become y into 1 by 3 y cube. It will be y cube by 6 plus c3y plus c4. Now, these are the two constants which we need to find. These two constants, if we find them and if we put them back into this equation, we will get the proper velocity profile. Now, for this, we have to use the boundary condition. And because we have from the velocity profile, we know that at both the end of the walls, that is at the hot plate and the cool plate, there is no slip boundary condition, that is at y is equal to minus b, the hot plate, no slip, vz is equal to 0. And at cold plate also, vz is equal to 0. No slip boundary condition. So after applying this no slip boundary condition, first we will put y is equal to minus b and vz is equal to 0. So we will get this equation. And after we will put y is equal to plus b and vz is equal to 0. We will get these both equation. Now from this we can subtract this equation to eliminate C4. So after eliminating C4, we will get C3. We will get C3 in terms of C2. C2 is again one constant which I had taken at the starting. We will get C3 as a function of C2. And if we put the value of, if we again add the equation, the previous two equation, if we add them, we will get the value of C4 in terms of C3. And After putting that and putting the value of C1, C2, C3, and C4, all the values, we will get this final velocity profile equation. So this equation is rho bar, that is the average density, into g, acceleration due to gravity, into beta bar, that is the uh, average coefficient of volume expansion, and delta T, it is the temperature difference, and B square, B is the half of distance between two of the plates, and mu is the viscosity, and y by B whole cube minus y by B plus B square by 2 mu plus B square by 2 mu into dP by dz. This is the constant we were talking about earlier. This will be C1, oh sorry, this will be C3, which we found out, and this will be C4. This whole term will be C4. And dP by dz here is the pressure gradient, and into rho bar into G to y by B whole square minus 1. So now we will summarize that how we got this equation, this final velocity profile, how we got it. So to summarize how we got the velocity profile equation. First we had this equation. First we had this equation, and here rho, it will have another expression which we will get from the Taylor series. Taylor series, we got this expression of rho. We neglected the higher and second order terms. Again, then we introduced the coefficient of volume expansion, and after introducing the coefficient of volume expansion, we again write another definition for rho, and beta again is defined as 1 by v into dv by dt. So we defined beta here, and after getting the beta, we put it in our equation, that is rho g. Rho g can be written as rho bar g minus rho bar into g. That is, we substituted this expression and neglected the higher order terms. And after doing that, we next substituted the temperature profile in our previous equation. So we got this equation. From this equation, these are the major components. First, we assume this one and this one to be constant for ease of integration. These both terms for ease of integration, we assume them to be C1 and C2. And we integrated this. And after integrating, we again got two constants, C3 and C4. Next, we applied the no slip boundary condition, and after that we again got two equations. First, what we did is we subtracted both these equations. After subtracting both these equations, we got the value of C3, and after adding both these equations, we got the value of C4. Next, what we do is we substitute all the constants, and we got our final velocity profile equation.